Recording is rolling. It is Tuesday, April 7th. We're going to continue this review of rotational mechanics. Actually, we're about halfway through exactly. And we finished a lot of the static situations. So just things being in equilibrium. And we're going to move on to the more dynamics. You're going to see more like things in motion and angular acceleration today. Okay, of course, you guys have your notebooks out. You guys are taking notes. It's just similar to what we've been doing all along. Here's my plan tomorrow is I'm going to pull up some FRQs for you guys. And then Thursday I'll get you this review quiz. Okay, so it'll be just like the past review quizzes. Let you guys work in teams and all that. Okay, but make sure that you know what's going on. Check focus. Make sure that you have everything turned in. You're not missing any assignments. A lot of you guys turned in the most recent quiz yesterday, the energy momentum, and so I got that graded last night or so. Turn that in. Turn it today, then grade it as soon as I can. Ooh, we got like coming up pretty soon. Take this weekend at 9th, 10th, 11th. We're going to do that. There you go. All right. So let's switch over to PowerPoint.
Why did you?
We gotta watch it.
Yeah.
All right. There we go.
Yeah.
All right. So.
Tend to forget. We know watching.
Guys, look at the scenario. I have a turntable here that can rotate about its central axis. That's dashed off there. Okay. And it looks like I wound a string around, and I'm pulling with some tension force here. So, guys, is that going to cause this to speed up its rotation? Faster. All right. Okay, so, in your notes here, jot down that picture real fast and fill in as many of these boxes as you can. Okay. Now, I imagine if you see the scenario, which guys, almost certainly you're going to see some version of the scenario on the AP exam. Okay. I imagine AP might give you this detail I put in parentheses. See where it says no friction with the central axle? Right. That's not necessarily true, but a lot of times for this class AP1, they'll make that simplification. Okay. All right. So start from the top here. Oh. The very top box, tau, you guys know stands for torque. Is what cross what again? R cross F. There you go. R cross F. Now, if you do have a string wound around this turntable and you're pulling with some tension force, is this force going to naturally set up to be perpendicular to this radial distance every time? Yeah, it doesn't really matter what direction you pull the string. This will be a right angle. All right. What's well, as long as you're pulling along the plane, right, along the plane of the turntable. Right. Now, if you have a net torque, and if there's no friction with the axle, wouldn't the applied torque be the net torque? Right? And if there was friction with the axle, could you just subtract out that torque so you end up with some net torque? Right? Or guys, what if you have lots of strings around and you have lots of people pulling in lots of different directions? You could eventually find the net torque, right? Right. So like add them if they're all going the same direction, all counterclockwise, and subtract them if they're saying clockwise or something like that. Right? Once you get a net torque, that's equal to what times what? I alpha. Right. Guys, could this turntable have some rotational inertia, capital I? Right? Which I imagine AP would probably give you. Right? But if you had to, could you derive it as 1/2 mr squared? Whatever the mass of this turntable is, whatever its radius is, you say, well, if it's a solid cylinder, it should be 1/2 mr squared, right? Right. Might have to. Right. So put these two boxes together, and you'll get this box at the bottom. What cross what is equal to what times what? There you go. Okay. So if I know the radius of this turntable, and I know the tension force I'm pulling with, and I was either given or I figured out the rotational inertia of that whole disk about its central axis, I could solve for, what does this alpha represent in physics? Angular acceleration. Oh, that's the rate that it's speeding up spinning in radians per second squared. Guys, what did I just tell you guys is the units for alpha? Radians per second squared. As long as everything else is like meters and newtons and so on. I should be kilogram meter squared. Right. But there's one box we haven't mentioned yet. That's this top box up here. Guys, as it's speeding up spinning, well, for any particular angular velocity, I did mark an angular velocity here, some omega, although that would be changing. Right. But it's only instantaneous moment. Right. L is equal to what times what? Omega. I omega. Yeah. Guys, isn't that analogous to P equals mv? This is angular momentum. So this is momentum in an angular sense. It's like if you spin a top and the top stays upright, it's related to that. Right? Or if you spin a coin, it's spinning on its side. Versus if you just like try to prop up a coin, it falls over. But if you spin it, it has its angular momentum that wants to be conserved. Right? You guys remember all that? You guys good on that slide? Right. Right. So a lot going on there. It's a pretty comprehensive slide. All right, let's focus on this angular momentum. Get ready for the next slide. Angular momentum. Right? And a classic scenario that's going to show up somewhere on the exam is this ice skater scenario. Right? You guys watched Winter Olympics recently? You guys see some figure skating? Now, if they go into a slow spin, and like this picture on the left, right, and then they pull their arms in, what happens to their angular velocity? Increases, right? Now, the guiding principle here is what's conserved. What property is conserved? Angular momentum. So that I times omega, right? That's what's conserved from the picture on the left to the picture on the right. Right? Okay. So I times omega equals I times omega, right? But it's a different I, it's a different omega. Yeah, so if you decrease your sort of average radius, you think of that, yeah, the rate that you're spinning is going to speed up. How about this? Guys, what is rotational kinetic energy equal to? It's not on the slide. 1/2 I omega squared. Right. Now, suppose you do energy accounting. You say the left picture, I'm just going to sum it up. Suppose it's like 100 joules. Would the picture on the right be also 100 joules, less than 100 joules, or more than 100 joules? Guys, let me repeat that question. I want to see show of hands. So let's say you did rotational kinetic energy, which is not a formula that's on the screen here. And that's 1/2 I omega squared. 1/2 I omega squared could be rotational kinetic energy. Okay? And let's say you do that energy accounting, and the picture on the left with the slow spin rate is like 100 joules. With the picture on the right, we're going really fast, but pull their arms in. 1/2 I omega squared. Would that be also 100 joules? How many guys say that would? Okay, that would also be 100 joules. Who says that? No, nobody says that because it's not conservation of energy. It's conservation of angular momentum, and that's different. Okay? Who says it's less than 100 joules? Does anybody say less than 100 joules? Does anybody say more than 100 joules? Yeah. All right, there's my winners right there. Got a win in class. More than 100 joules. Okay? So once you plug in all the numbers, yeah, it'll always be more kinetic. Wait. Hold on. Did I just say there was more energy later on? Where'd that energy come from? Was it just created out of nothing? No. That would be a violation of conservation of energy. The energy came from somewhere. From the skater's muscles. Yeah. Eating Wheaties that morning. Breakfast with champions. Yeah. And their muscles. Chemical energy. Right, so on the theme of something to do with angular momentum and conservation, do you guys remember this? I know this question popped up in one of your quizzes. What if I have a ball of clay and I drop this onto this already rotating turntable? Now, after this clay sticks to the turntable, does the turntable spin at the same angular velocity or faster or slower? It's gotta be slower, right? Right, because we just increased the overall mass of the overall rotational inertia. You can say it too, right? Now, guys, it's the same guiding principle as the last slide. Angular momentum is conserved, and angular momentum is I times omega. Right, so there was some initial angular momentum, which was just I times omega for the disk rotating. Right, and after this ball of clay lands on it, it's the exact same amount of angular momentum, but it's a different configuration. Because now you have the I of the turntable, plus you also have the md squared for that point mass. That adds to the rotational inertia, doesn't it? That's all in parentheses over here. Okay, okay, and then that'll be times some omega final, which would have to be smaller, like slower. Right? You guys get the guiding principle there? You see that? Right? Because to finish this off, all you need is just a little bit of algebra, a little algebra shuffle. Go and do the algebra before I give away the answer. Can you guys solve for omega final? Right. You guys can do some algebra, right? All right, there you go. There's the answer. Is that what you guys got? Yeah, you guys follow that. You guys can do that algebra, right? And of course, if you add numbers, so you can plug in the numbers, then you get some numerical answer. All right, you guys go with dropping a ball of clay on turntable. Okay. You guys remember for a point mass, the rotational inertia is like mr squared. In this case, md squared. You guys remember that from yesterday? Right. Ooh, guys, AP asks this question about every year, so you're going to see some version of this question. There's different variations on this question. I have a graph version here, okay? But here we go. What if you have these two disks, and one of them is already rotating? Looks like I have the green one has double the rotational inertia of the gold one. You guys see that? Maybe it's like twice as thick or something. Okay? And it's already rotating some omega initial. Okay? And there's this OA stationary disk, this gold disk, that we're going to slowly lower onto the green disk. And then there's some coefficient friction, so they're going to stick together. Right? You guys get that? Right? Right. Now, guys, what was the guiding principle of the last two slides? What's conserved? Angular momentum of the whole system. So I know I can say for the two disk system, whatever this angular momentum is going to be the same all the way across. Okay? But I have some special time marked out here. And this is the time that the two disks are going to start sticking together. Okay? Okay, so we're going to slowly lower that gold disk until it lands on the green disk. Okay? And then what? Okay. Now, guys, this whole graph is in terms of angular momentum. And you know that the total angular momentum of the two disk system is conserved. Okay? But there's some more curves that are going to be on here, which is for each disk. Right? So the green disk was already rotating. In fact, the green disk was supplying all the angular momentum there was to start with, wasn't it? Right? And that gold disk wasn't spinning at all, so you can call that basically zero angular momentum. Because I times omega, well, omega was zero, so I times whatever, I times zero is zero, right? Okay. Now that was before they stuck together. Now after they stick together, go ahead and finish that graph. So in your notes, and there's a lot going on there. So give you guys a minute to catch up, finish drawing that picture and the scenario, and jot down whatever notes you need. We're taking that stationary gold disk, we're going to drop it down to that already rotating green disk, which looks like twice as thick. Yada yada. Right there, that graph started, angular momentum as a function of time. It looks like during the first few seconds, right, just the green disk was rotating, and that gold disk not yet. Right? But then at that T drop, they're going to stick together. And I haven't finished the graph on the screen yet. But I want to see if you guys can get it first. So take a trip around the room here. And see who's able to finish that graph correctly. All right, we really have to think deeply on this one.
Oh, set. About.
Right, who's going to get these graphs? Ooh, close, close. Right.
Close.
Lily's really close. Right, Justin's really close. Right, Austin's really close. Nathaniel's really close. All right, Logan got it. Exactly. Lincoln really close. Oh, Lincoln really close. Right. Okay, there's a lot of you guys who are really close would have been exactly correct if this just had been the same rotational inertia. Right, if they'd been the same rotation, but they're not. You guys see that the rotational inertia is ratio 2 to 1? Okay. In fact, what about this? Guys, let's take things to extremes. What if this green one was made out of lead? It was really thick and heavy. Yeah. And this gold one here was made out of little flimsy cardboard. And you drop the cardboard onto that lead disc. Okay. Would the whole system slow down a tiny, tiny bit? Yeah, the screen would slow down a tiny bit, but hardly at all. Okay. So do you guys think that maybe the screen would go like barely change at all, it would just drop down maybe a tiny bit, and this gold one would pick up exactly that amount? Okay, so something between that and them being the same rotational inertia. Okay, so something between those two. Okay, can you guys interpolate? Okay. In fact, guys, if they're ratio 2 to 1, if they stick together, do they have the same final angular velocity? Yes, they do. They have the same angular velocity, that omega. There's an omega. Right. So omega final would be the same for both. Right? But they have different I values. And the I values are a ratio 2 to 1. And L is equal to I times omega. Well, if L is I times omega, they have the same omega. But the I's are a ratio 2 to 1. Then how do you think this graph finishes off? Boom. There you go. Okay. That's for that scenario. Okay. And as I was walking around the room, a lot of you guys had them as the same final angular momentum. So you had this green, this gold line, right? And that would have been correct if the two disks had the same rotational inertia. If it had been I and I, or something like that. All right. Any questions about those disks? So AP is almost certainly going to ask you some version of that question. Oh, also this, this also comes up every year. So what's the angular momentum of a point mass? So what if I have a point mass like this ball of clay here and I just throw it? Right. Now guys, could this have some regular momentum? What's the regular momentum of this equal to?
MV.
Yeah, MV. That's just regular momentum, right? It's got to collide. So as soon as I say that collision, okay, it's something to do with momentum. Right? But here's the twist on this is that this whole stick is gonna rotate about this joint right here that I marked with an X. You guys see that pivot point, right? And I think there was a quiz where I gave you there was a whole paddle wheel. Do you guys remember the whole paddle wheel? It's the same equation, right? But oftentimes I see AP give you guys a stick. Here, so I gave you guys a stick here. Okay? Right. So the question that this might lead into is like how fast does this whole stick rotate afterwards? And it really depends. Does this ball of clay stick to it, or does it bounce off, boing? Because that would give you different results. Okay. But this side, we're gonna set like how to think about it. Like what are the guiding equations here? Okay. Okay. So what do you guys put in that gold box up here? What's the angular momentum of a point mass? MVR. Yeah, it is MVR. Yeah. Right, so R cross MV. Right? And I've always seen the question where on AP exams where this point mass comes in at a right angle to the stick. Do you guys see how it's coming in at a right angle? And guys, the cross product of a right angle, isn't that just sine of 90 degrees, which is just one? Right. So yeah, so it's always MVR on an AP exam. MVR, RMV. Okay. Okay. Now, what do you guys think goes in this pink box right here? Yeah. So something about I times omega. So L is I omega. Right. So if it was some version of that. I think if I remember right, the recent quiz question I gave you guys, the ball came to a dead stop and like bounced off, and it like sent the paddle wheel into motion. Okay. And from that point of view, you can interpret that as all the angular momentum went into the paddle wheel, and whatever the I of the paddle wheel was, you could just put for here, right? And then this was MVR goes here, and then you could solve for this omega for the paddle wheel. Right? If the ball, guys, what about this though? What if the ball of clay sticks to the stick right here, or sticks to the paddle wheel? Right? Would this I right here be the I of the stick of the paddle wheel plus the I of this point mass? And what's the I of a point mass again? MR squared. Right? So this I, you could open up some parentheses and say, well, it's really the I of the stick plus the MR squared of the ball of clay. It's that whole expression right there. I think AP's asked exactly that question in the past. Right? All right, let's go to, here, I'm going to go back a few slides. Go back. Right. Here's where we started today, right? You guys remember this? Right, so let's say you're pulling with a constant tension in the string. So I'm pulling with the constant tension. And this radius is also constant. So would that be a constant torque? Right? So constant string tension, constant radius. Okay, so I have a constant torque. So is that just speeding up spinning? Right. All right, now let's complete. Let's go back to these graphs here. Okay, now we're back. So we have two perspectives on that same scenario. And we just went over torque as a function of time and angular momentum as a function of time. And I'll give you guys the torque graph because let's just say you have a constant torque. Right? So constant torque. Right? What does the angular momentum as a function of time look like? Let's see who's going to get this. Who's going to get this? There's a relationship between those two graphs. What is that relationship? Oh. You figure this out.
Oh no, wait, no. I understand it now. I understand it.
AP asks this question every year too. Yeah, Justin got it.
Yes.
Yeah, Sully got it.
I almost messed it up.
I got at least two winners.
I almost said constant. No.
Yeah. Guys, you're pretty much guaranteed getting asked the question. Because AP asks this question every year. Yeah, Gunnar got it. All right.
You know what I mean? Let's try to draw it.
Okay, so I got at least three winners. I hope I didn't miss anybody out there. But we're applying a constant torque. Doesn't that mean that disk is speeding up spinning? You guys, L, angular momentum. What's the formula for angular momentum again? I times omega, right? And that I is pretty much constant, but that omega is increasing. Oh. If you have a constant alpha, because I have a constant torque, then I think that omega is increasing at a constant rate. What does increasing at a constant rate look like? That right there. Right there. His answer. Okay. So this graph on the left pairs with this graph on the right. Okay, so these two go together. If you know one of these, you know the other. Okay, and then here's the relationships too. So if you integrate torque versus time, so the area under the curve, which for this example is just a simple rectangle. right? That will tell you the change in angular momentum. Okay. Do you guys see, guys, what if I split this up into 3 seconds? Got second 1, second 2, second 3. Do you guys see that? 3 seconds? Right. Aren't those equal size, skinny looking rectangles? You see that? Right. So over on L versus T, I increase some amount, then I increase that same amount, then I increase that same amount. You see it's increasing at a constant rate. It's the same thing. Right? Or if you go backwards, right? But let's do the derivative version. The rate change of angular momentum is called what? Torque. Yeah, slope or torque in this case. Right? You guys see? Hey, is that a constant slope? It is a constant slope on L versus T. That means a constant torque. Oh, okay, so a constant coordinate on the torque. It's the same thing. You see that? Guys, here's a twist that I do remember AP asking in the past. What if, guys, are you guys ready for this? Guys, you guys ready for this? Here's a question AP's asked before. What if it's a non-constant torque? What if you have a torque that's actually linear? Do you guys see my mouse cursor is tracing out a linear shape? You guys see that? Right. If that were the case, then what shape would this graph be on the right? Parabola. Yeah, it would be. Yeah, it would be a parabola. Yeah, sure would be. Okay. That's been a question in the past. Okay? Okay. So are you guys okay with those two graphs are related? Okay. Right, so one more look at this, because this is going to lead to the next slide. Guys, the next slide is going to be pretty much this right here. The change in angular momentum is torque times time. Do you guys see that? Change in angular momentum is torque times time. Okay. All right.
Try and graph every point.
Now you can solve this. I'll give you the first line. First line is changing angular momentum is torque times time. Okay. So here's the scenario. I got a basketball. I'll give it a little kick. Pow. That's some force at, of course, the radius of the basketball. Okay. And that's going to cause it to spin. It's going to cause, I'll give it an angular velocity, omega. And, it looks like that's the question. Because I gave you guys a setup and then a bunch of space. And then the final answer is going to be, how fast is that basketball spinning? Go ahead. See if you can derive the whole thing. In terms of I of the basketball. And you know what, guys, suppose you also had your rotational inertia table. Maybe they give one to you. Is the basketball basically a spherical shell? A spherical shell? Right. Does anybody happen to remember from yesterday the rotational inertia of the basketball? 2/3. 2/3 of r squared. Oh yeah. 2/3 of r squared. Right. So that might be helpful. But you're not really expected to memorize that though. Yeah, but I for a basketball, I for a spherical shell, could be 2/3 of r squared. There you guys are doing on this derivation here. Okay. How fast is that basketball going to be spinning? How fast?
All right.
So I equals 2/3 of r squared. It's going to show up on the PowerPoint eventually. All right, how fast is that basketball spinning? Right. And if you have the answer and you're checking your work, see if the relationships between the variables make sense. Right. Like, how about this? If I kick this faster with the greater force, pow! With a greater force, should it be spinning faster? I think that would make sense, right? Right. What about this? What if I apply 3 forces? What if I go pow, pow, pow? Isn't that basically tripling the time interval? Right? If I hit it 3 times, it's like tripling the time interval. Should that make it spin about 3 times as fast? Okay, so that's probably a direct relationship. I think there should be a direct relationship between the time and the angular velocity for that reason. Right? How about this? Guys, what if you replaced this basketball, this regular basketball, with a basketball with a lead surface? What if you have a lead surface basketball? So it's the same basic shape, okay? But the surface is really, really massive. Is it more difficult to get it to spin then? If it's made out of lead surface? Yeah. So I think the more massive or the greater the I, that should slow it down, I think. Okay. All right, you guys ready to go through the derivation? You guys ready? All right, here we go. Here we go. Okay, so what can I replace for this torque? This is what times what? R cross F. And what can I replace for, let's suppose it starts from rest. If it starts from rest, we'll just call this L. L is equal to what times what?
Omega.
Omega? Right. Did you guys get at least that far? Right. That might be just a point right there. Like, oh yes, you did the correct substitutions. That's a point. Bing! You pick up a point. RF T equals I omega. as long as it starts from rest.
Artist? That's point.
Hey.
You still do.
Hey. Now, what did I tell you guys for a basketball? It could be equal to I. 2/3 MR squared. Okay. Something like that for a basketball. Spherical shot. Okay. Alright. Now, last step is going to just be algebra. Algebra. Yeah, I'll give you guys a shot before I give you guys the answer. Make sure you can do the algebra. Just do a little algebra switcheroo. Solve for omega. How fast is that basketball spinning? Make sure you can do the algebra. Algebra.
See, it's the one word in the
Alright, what'd you guys get?
That's 0. Oh.
Boom, there's the answer. There's the answer.
That's what I got.
Hey, look at that. Guys, if you kick it with, suppose 3 times the force, is it going to spin 3 times as fast? Yeah, it's a direct relationship. Suppose you give it 3 kicks, pow, pow, pow. So you effectively triple the time interval. Is that also 3 times as fast? Yeah. What if you replace that regular basketball skin with lead skin? Would that make it spin slower? Yeah, because M's showing up down here. Okay. Now, guys, the kind of tricky one is the radius of the basketball. Guys, what if you had a small basketball versus a big basketball? Guys, which would, all else equal, which is going to spin faster? The small basketball or the big basketball? The small one. How'd you know? Well, I was looking at this radius, really. Yeah, this radius. Yeah, but also on the bottom. Yeah, so AP would call that functional dependence. They say if you recognize, yeah, again, all else equal.
It's smaller, but it has the same plan.
Yeah, the fact that this radius shows up on the bottom. Okay, the small basketball spins faster. All right. All right, so we're back to, we have a string wrapped around a turntable and pull in with some force. Okay, and it's going to rotate some angle. And guys, would there be some energy transfer from you into the disc as you're turning it, tries to spin?
What?
Right. So do you have to remember work as force and resistance? You guys remember that? But let's do some substitutions here. So in place of this D, can I say it's R theta? Do you guys remember that? R theta? Could be that D right there. Right. And then what if I categorize these variables differently? What if I organize them? So R cross F. Hey, what is R cross F?
The torque.
That's torque. Okay. So torque times angle. Yes, torque times angle represents the amount of work that you did rotating that disc. Okay. That is one of the formulas on your page. Okay, so I'm going to do the derivation for the slides, but it's wait, where'd it go? Oh, it's right here. It's right here. Is the work equals torque times the change in the angle? Torque times change in angle. It's right there. Okay. But that's where it comes from. All right. You guys good with that? How about this? Let's do some numbers. What if torque is equal to 10 Newton meters? You guys got that? Torque is 10 Newton meters?
Yes.
And theta is 30 degrees. Okay. So I got 10 Newton meters and theta is 30 degrees. Okay, so I'm going to calculate it. You guys calculate it. Right. How much work was done in joules? Here, I'll say these numbers again. Torque is 10 Newton meters. Theta is 30 degrees. All right, how many joules of work is that? You got 5.24?
Yeah.
Joules? That sounds right. 5.24. Okay. Okay. Because guys, here's torque is 10 Newton meters. Here's 30 degrees, but are you allowed to put degrees in that equation? No. What do you have to put? What unit? Radians. And how do you go from degrees to radians? Times pi over 180 will do it. Right? Can you guys convert from degrees to radians?
I didn't know that.
Right? Well, we're going to do times 2 pi over 360. It's the same thing, isn't it? Times 2 pi over 360. Okay. But yeah, you have to use radians. It has to be in radians. Because if you ever directly multiply an angle, and it's not sit inside a sine or cosine, nothing like that, has to be in radians. Oh, here's a good clock question. If AP doesn't ask this, you'll probably see this in college. So it looks like I have a guiding principle here of confirmation of angular momentum. Okay. Here's the scenario. I got a ball on a string. You guys see a ball on a string? And I'm wheeling it around in a circle. And then I start pulling on that string, and I'm pulling it in. And the ball starts to follow the spiral pattern. Okay. Now, do you guys think that that ball is actually going to be, like if you point a radar gun at that ball, is it speeding up? Is it going faster, faster, faster the more you pull it in? It turns out it is. Maybe kind of like the ice skater. The ice skater was spinning faster. I remember that. Right? So I wonder how much energy was done pulling it in while it was spinning in that spiral. How much energy was done? It take from your muscles. Do you guys get that?
Tornadoes.
Okay. So start with angular momentum and say that's the guiding principle here. That's what's being conserved. So I got this M. Do you guys remember for point mass? It's MVR. Just remember that, or R cross MV, whatever. Okay. Okay. So we'll start off with radius of 3R, and we'll end up with radius R. So we got like that. Okay. So therefore, I can say how fast does it end up compared to how it started? And it ends up being just the same ratio backwards. Okay. Okay, you guys good there? It's going 3 times as fast in a linear sense. Okay. Okay. Now go ahead and fill out that gold box. You guys go ahead and
Not ready for mine.
figure out how much energy it takes. How much energy does it take? Pull that ball into a spiral. What's the formula for rotational kinetic energy?
No.
1/2 pi omega squared. That sounds pretty good. All right. Oh, you know what? I see a lot of V's up there though. What is it in terms of V?
RV.
1/2 mv squared. That might be more useful actually. Now I'm thinking about it. Might be 1/2 mv squared.
No, beta. It's got there. Okay.
How much energy did it take to pull that ball into a spiral? Take some effort from your muscles. And so the work would be the change in kinetic energy of the ball. The change in the kinetic energy of the ball. Well, that energy had to come from somewhere. Oh, and that was the work that you did, pulling it into a spiral. And oh, guys, what is V final compared to V initial? How many times? 3 times. And that came from this conservation of angular momentum that we did up here in the blue box. Right? Now, guys, that V is being squared. So what's the factor of 3 squared?
9.
9? Okay. So I think that ball has 9 times the energy at the end than it did at the beginning. If you're pulling it in. 9 times the energy.
100%.
So if you subtract, you get 8 times for the difference. It's 9 minus 1. Guess where that 8 comes from? That's 9 minus 1. Right. Now, everything in brown up there is particular to this exact question where the final radius is 1/3 of the initial radius. Okay. But of course, if you change that, then everything in brown would change to different numbers. Right.
Where did the 8
Well,
9 and 1. What is it? 8?
9 minus 1.
I got that. Got that. You weren't even thinking of that.
All right, well, gotta move on here. You guys know this presentation's posted, this video will post later. All right, so have all that. Okay, guys, this slide and the next slide are both the same scenario. I'm gonna have a bucket on a disc. Now, guys, this disc does have significant rotational inertia. You guys see this eye? Okay, it's not a massless disc. Okay, and let's say you release this bucket from rest and it starts falling. Now, this slide doesn't really lead in any particular direction. It's kind of an exception to most of these slides. But can you guys write as many formulas as might apply to that scenario? Okay. So this could go a lot of different directions. I'll give you guys some examples. You could ask the question, how far does the bucket fall as a function of time? You could ask, what's the acceleration of the bucket? You could ask, what's the angular acceleration of the disk? You could ask, how fast does the bucket fall as a function of time, maybe after some time interval. You could ask, how fast is the bucket falling after some distance falling? And actually, that very last question I just said, how fast is the function of distance? You could solve this much more quickly through conservation of energy, and that's the next slide. Okay. But how about this slide? All right, so let's go fill in the blanks here. What did you guys write in this top box? RF equals what? Yeah, torque, which is, okay, suppose there's no friction with the axle. Do you guys see there's no friction with the axle? I'm just making up. Yeah, I alpha. Right. Okay, so that's the torque applied. Okay. Guys, guys, do you see the tension in this rope right here? See if you guys get this. Guys, is the tension of the rope exactly equal to the weight of the bucket? Yes or no? You're right, it is not. It is not. Guys, which force is a little bit bigger? The weight of the bucket or the tension force? The weight of the bucket. Because the bucket is accelerating down. It might be kind of slowly, but it is accelerating. Okay. And notice which force is here, which is the tension force. Okay. Speaking of the bucket, let's focus on the bucket for this next equation. What the difference between what and what? What minus what equals m times a? What minus what?
MG minus tension force.
Yeah, mg minus tension force. The weight says let's go down. The tension force resists that. It says no, pull them back up. There's some difference, and that difference is the net force in the bucket, which results in the acceleration of the bucket. You see lowercase m represents the mass of the bucket. Okay? And what are some other relevant equations? Like, for example, guys, look at this alpha here. Is this alpha the angular acceleration of the disk? And this a is the linear acceleration of the bucket? Are those related to each other?
Probably.
Is this alpha and this a related? How are they related? Guys, what very short equation relates this a to this alpha? R. You need R. R. Okay, yeah, you said that. All right, there you go. Okay. Okay, so if you want to know how far, how fast, or acceleration, if you have the angular value, multiply by R, you'll get the linear value. Or vice versa. If you have the linear value, divide by R, you get the angular value. Okay. Right, do you guys remember these for turntable physics? This disc looks like a turntable on its side, doesn't it? Yeah. Right. Right, these last boxes are kinematic formulas. So do you guys remember the 3 kinematic formulas? No, those are linear, so this applies to the bucket. But what about the disk? Should I maybe apply the angular versions for the disk? Okay. And of course, they're related to each other by these right here. Okay. So again, I just spat a bunch of questions to you guys too that could also pertain to, right. So this could lead a lot of different directions. You guys got that? Now this next slide, hey, it's the same guy all over again. Okay. But a very specific question. Guys, here's the question again. How fast is that bucket moving after this height change? So maybe it falls like 1.5 meters. Now, how fast is it moving? That's the last question. V equals what? So, and I'm giving you guys a hint here too in the title. Use conservation of energy. So specifically that method. So go ahead. The very first line is a conservation of energy equation. Go ahead and set up a conservation of energy equation that applies to that scenario. Conservation of energy. Let's say, don't worry about friction with the axle. There's no friction with the axle.
Well, it's circle. Right. No, you're right.
Can you guys craft a conservation of energy equation for that scenario? Alright, also got it. Alright, who else is gonna get this?
That's right.
They got this here.
Oh,
Working on it.
What are you doing?
Okay, got it.
Stop solving things. Let's go do things.
Justin got
We did
it.
not start with things. No, yeah, there's no routine.
Close. You're just one thing. You got part of it.
What do you got? Yeah.
Alright, Lovey got it. Who else?
There's no substitutes.
Oh, you're almost there. Almost there. Okay.
What did you miss?
I think okay. Some of you guys got it. Some of you guys are really close or have parts of it. Okay, guys, here's the answer. Okay, conservation of energy. All right, there's the answer that I was looking for, and some of you guys got that. All right, here's why. So this bucket starts elevated, and that bucket's going to fall. Guys, doesn't that mean the bucket started off with a bunch of gravitational potential energy, MGH to the bucket? That's MGH for the bucket. Right? Now, as it falls, it's losing that gravitational potential energy. That's turning into 2 other kinds of energy. It's given the bucket some speed, some kinetic energy, 1/2 mv squared. Okay. And also, this disk is rotating, so that's 1/2 I omega squared is routed into rotating that disk. Right? That does have a significant rotational inertia. Okay. Right. Okay. You guys go with that. Now, I think the next step is, guys, is this v the linear speed of the bucket down? Is that related to this omega? How fast the disk is rotating? And guys, what is that connection? Guys, isn't this v equal to omega times r? Right? You guys hear Lily? V equals omega r, right? But you know what? I don't actually want to substitute that way. Here's why. Because the very final line says v equals something. If I substitute out the v, then I've lost my v. Maybe I could go back and re-substitute later. Right? But maybe I could substitute out this omega instead. So what is omega in terms of v? V over r. V over r, right? Okay, now it's being squared, so everything's being squared there. There you go. That's all I did from that line to that line. I just substituted omega with v over r, and then we're squared it. All right, and there's one step left, which is the final answer. So go ahead and do algebra. Everything else is just algebra. Go ahead and solve for v of the bucket. How fast is that bucket falling? Can you do some algebra? Everybody's just doing some algebra. We're pretty much done with the physics. It's just algebra at this point. Can you do the algebra? Solve for v.
You solved it perfectly.
Ooh, looks like I must have skipped a step or two from here to the end because I think you have to factor out the v squared. Can you guys factor out the v squared first? Right? Can you see it? You can factor out the v squared.
Oh, yeah.
You can. Yeah.
You know what? I'm gonna write this down on paper and here, you guys keep figuring it out. Get a head start because I'm gonna flip the screen over here pretty soon. So I got that equals
Mr. Griffin, I don't want to.
that. A squared over. Sorry. Okay. I just wrote it down on my paper. Let's flip my screen over and walk you guys through. Okay. So if we're for this, okay, you're trying to solve for this v, which shows up here, but also here. Okay, there. Okay. So I'm going to factor that v squared out. So I'll say mgh equals, that gives me a 1/2 m plus a 1/2 I over r squared, I suppose. And that's all times v squared. Okay, can that be true? Now can I take everything in parentheses and divide it down?
Yeah.
Yeah. It's mgh over. Can I pull a 1/2 out? Is that okay? Pull 1/2 out. So it'll be 1/2 here, and then be m plus I over r squared. Okay, this is equal to v squared. Okay. Now a couple of things at the end here. Okay, so if I'm dividing by half, am I allowed to take this 2 and flip it back up top?
Yeah.
If you're going to do that PowerPoint. Okay. And then what's the very last algebra step? You have to do what? Square root. Okay. So I'm going to do square root. I think this 2 is going to show up here eventually. And then mass of the bucket plus rotational inertia of the disk over r squared. Okay, and that's equal to v. Okay. That should be the answer right there. Okay. And that's just algebra. So everything leading to that was the physics, and then that's the algebra. Okay. All right. Yeah, that's it. That's it. Okay. All right. How about? Oh, here's another classic question. Sometimes they like a toilet paper roll. If you have a toilet paper roll, and you hold the paper and let the roll fall down. Okay. And so, guys, a couple of perspectives here. I'll show you the tricky way first, guys. The tricky way is so something to do with torque. Guys, is this as it falls? Is it actually rotating about the center of the cylinder, or is it rotating about this point on the edge? Point on the edge, which means I have to bring in the what theorem. The what theorem? Parallel axis. Parallel axis.
Oh
no! Is there a parallel axis? And so torque could be R cross force, right? And the force I'm going to use is mg, the actual weight. Right? This is not the only way to set this up, but it's the way I prefer to do this. Okay? But if I do that, I picked the pivot point as the edge of the cylinder. And since I did that, the rotational inertia of the cylinder is actually its own rotational inertia about the center, which is 1/2 m squared. Plus, in purple is the parallel axis theorem. And so that's I, and then I got the alpha. Okay? And so then I can clean this up like this. Okay? And I can solve for the linear acceleration of that sphere. Okay? Which, for this particular scenario, always ends up being 2/3 of the gravity field of the planet. Okay? 2/3 of the gravity field of the planet. Okay? Now, if I wanted to answer a different question, like how fast is it falling at some particular moment? Well, let's do it in terms of height falling. Okay? If I want how fast is a function of height falling, I need to bring in kinematic right here. Which kinematic formula could tell me how fast is a function of height? First, second, or third?
That one.
Yeah, how about that third one?
That one.
The one that doesn't mention time. Okay, so because I'm looking for as a function of distance fallen, which is that x right there. Okay, so if I do that, I'm just going to substitute this a could be 2/3 gravity. We got that from all this torque analysis. That can tell me how fast it's falling. You see that? Okay. Okay. Now I have to go kind of fast here because I want you to just see big picture on this one. Okay. But the next slide is the same scenario. Guys, the same scenario. But we're going to address that specific question first. How fast a function of time falling with conservation of energy? right? And then we'll use kinematic to solve for acceleration later. So it's kind of backwards because it's going to be backwards. Right? Now, guys, the nice thing about energy, or one nice thing, is you don't actually need parallel axis theorem. Because if you use the energy method, parallel axis theorem doesn't actually show up. Okay, and then you get the same speed as we got before as a function of height. Isn't that the same answer as before? Okay. And then you can go back through that third kinematic formula and solve for the acceleration. Of course, you get the same acceleration we got before, but it's all backwards. Guys, that? All right, guys, good? All right. Now, the last few slides are all basically the same idea. Is I got objects rolling downhill. Let's do the basketball. Now, for the basketball, it's it goes like this. Okay.
no.
But guys, look at this 5/3 right here. That's also parallel axis theorem. You guys remember a basketball is spinning about its center is 2/3 m r squared? So if you see 5/3, it's because it's actually spinning about this point. But this is using torque. Using torque, you can get the speed of the basketball is that right there. You see that? Right. But there's a much easier way to solve this, which is not to use torque, but to use conservation of what? Energy. Okay? And this is a much easier way to solve the same question. Right. And this one, you don't need parallel axis theorem. Look at this 2/3 here. Hey, isn't that just straight off the table? Okay. Because now I'm looking at the center mass of the basketball for the energy analysis. And I get the same answer. It's the same answer. Okay. Right. So I got all these different balls rolling down these inclines. So I think I solved them all for you guys. Right, they're all here. All the balls. All the balls. All the balls. Even a mystery ball.
Oh, the mystery ball.
Just in terms of I. In terms of I. Now you got all of them. Right. Do you guys remember the racquetball challenge? Oh yeah, it's slided. Oh yeah.
Mr. Griffin, what is that?
You all figure that
Now
out.
the AP time.
Roll race. Probably not that expensive. All right, guys, who wins the race? Yeah, the frictionless hockey puck wins the race. And then, okay, he goes over. All right, you guys have a good night.
Mr. Griffin, I'm gonna close my eyes to sleep tonight and see that.
Ah, yes. Pleasant dreamings.